Thank you for a warm introduction. Today I will talk about fault-tolerant quantum bus architecture. Maybe this term is not very familiar, just I'm mentioning that we are interested in transporting one quantum state to another state. So mainly I will introduce how to use this 3D cluster state to teleport one state in Q1 to another place like Q2. For introduction, I'll begin the talk with entanglement swapping. We are basically considering D repeaters, and they are arranged on a line, and they share one repeater state between neighboring repeater stations. What we do is just performing Bell measurements. And the post-measurement state would be, for example, psi st, where s and t can be computed using the measurement outcome of the Bell measurement. And we can represent this whole protocol using circuit identity. And more explicitly, we can write this in this form. So we have cat0 product state for the input, and we have so-called entangling circuit, and single qubit measurement is following. Here we see two properties of this circuit. So one is the depth of the entangling circuit is constant, meaning that it does not grow in terms of the distance d. And the other property is that we only allow 2 qubit gates within repeaters or between nearest neighbors. So for example, here we have CNOT gates between R1 and R2, or 2 qubit gates like this one is within this repeater station R2. Okay, keeping in these two properties, we slightly generalize this model like this. So we increase the number of qubits with this M, and we apply entangling circuit which has circuit depth constant O1, and then again single qubit measurement is following. And so why are we considering this model? Basically, we want to make this model fault tolerant. So we are basically interested in those 5 parameters. We are considering circuit level noise, which has strength P, and we want to achieve a large distance of the entanglement, and we aim high fidelity as much as possible, where the fidelity is just the overlap between the post-measurement state and psi alpha and beta, where alpha and beta are efficiently computable in classical machines. And we want to keep our entangling circuit with constant depth, and we want to use a small number of qubits per repeater stations as small as possible. Okay. Equivalently, we can write the previous circuit like this. So basically, I just replaced all the 2 qubit unitaries between nearest neighboring repeater stations using gate teleportation. So I replaced those unitaries with bell pairs between neighboring qubits like this. So those pre-shared bell pairs came from gate teleportation. So the number of bell pairs between neighboring repeater stations must be less than m times delta, where m was the number of qubits per repeater, and delta was the circuit depth. So this would be the input state, and and we don't have any 2-qubit unitaries between nearest neighboring repeaters, so we have LOCC and single qubit measurements are the following. Then we can give very simple theorem, which is we call necessary repeater size theorem. So let's say we want to make our final state satisfy fidelity which is greater than this number, 0.684, let's say. And if we have noisy input state, which is affected by IID depolarizing noise on pre-shared bell pairs like this, then to satisfy this fidelity inequality, distance of the entanglement should be less than or equal to this number. And in particular, we can say that the necessary number per repeater station is omega of log of d. The proof idea is the following. So we consider depolarizing noise on pre-shared bell pairs. And we know depolarizing noise is a convex combination of identity channel and entanglement breaking channel. So I visualize depolarizing noise as a single flash here. And we consider, okay, what if what if there is Rj and Rj plus 1 such that all the pre-shared bell states are affected by entanglement breaking channel. And then our noisy input state would be Rj plus 1 separable state. And applying LOCC doesn't really help us to get more entanglement. So basically, this is the main idea of the very easy theorem. And then natural question would be like, so what is the sufficient size of the repeater station? So here is our main result for sufficient repeater size. Let's say we are given any distance d and the number of qubits per station m. And then we can always give a certain quantum circuit q such that let's say our circuit suffers from local stochastic noise of strength which is below than a certain threshold where we estimate it by 2 times 10 to the minus 4. And then we can guarantee that the output of the circuit always satisfies constant fidelity f, which is always greater than 1 minus p over p0 if our entanglement distance is bounded by exponential in some constant time square root of m. Asymptotically, it says, okay, with this circuit, we can say that if we have m is equal to O of log square of d, then we can always say our final quantum state would satisfy this fidelity inequality. Okay. So far I didn't really explain what is our local stochastic noise is, but it was actually discussed in the plenary talk, but I will a little bit repeat it and then I'll move on to the actual circuit. So the local stochastic noise has the following definition. So we are considering n qubit Pauli error E, which has the probability of occurrence bounded by p to the size of the cardinality of the support of that Pauli error. And let's say we have the ideal circuit, which is nothing but U1, U2 up to U delta. And we measure out all the qubits except for Q1 and Q2. And we can write all the faulty gates or noisy input state or faulty measurement outcome with those Pauli errors, namely E in, E1, E2, up to E delta and E out. And we only request that the marginal distribution of these E1 to E delta and E in and E out to be local stochastic noise. The following lemma says that if our ideal circuit is Clifford circuit, then we can actually move all these errors to the end of the circuit right before the single qubit measurements. And the lemma says that this equivalent error E is also a local stochastic error with strength Q, where Q is in the function of P and delta. And what is good to know is that if we only consider constant depth, then Q is also constant. So we are going to use the proof technique that, okay, it is enough to show the threshold bound on the phenomenal side because we can deal with this general circuit level noise. Okay. And I should move on to the part what is the depth 6 circuit Q is. So I'll explain this in the terminologies that I've introduced before with entanglement swapping. So we are considering each repeater station as the cross section of this giant 3D aligned qubits. And I'm going to denote this width of this 3D structure by d. So m is nothing but theta of d squared. Okay. So the construction is the following. So we first prepare all plus states, and we apply CZ gates for every bond within the repeater station. And then you get so-called cluster state, which lives in each repeater station. And then you apply another CZ layers connecting neighboring repeater stations like this. So this is so-called cluster state, which was investigated by Rausendorf, Bravi, and Harrington in 2005. And what they did is actually they prepared this cubic 3D cluster state, and they analyzed what happens if we measure out all the black qubits here. So I denoted the classical results by S1 to SD. What they showed is that the post-measurement state is nothing but surface code-encoded Bell state with some Pauli logical terms, Z alpha and X beta, where alpha and beta can be computed classically using the measurement outcome S1 to SD. And what Rausendorf et al. Proved was that if they start this protocol with noisy cluster state affected by IID Pauli Z errors, this process is still fault-tolerant, and later Bravi, Gosset, Koenig, and Tomamikel proved that under local stochastic noise, the process is fault-tolerant. And later, Persegers in 2010 did some similar work. So what he did is what happens if we measure out all the qubits except Q1 and Q2. And he used what I call triangular pattern, such that he measured out all the blue qubits here with the shape triangle in Hadamard basis and all the white qubits in computational basis. What he showed is the post-measurement state is a Bell state with Pauli correction Z alpha and X beta. And he also showed that with this LOCC model, where I replaced all CZ gates between R2, R1 and R2 and so on with Bell pairs. So if those pre-shared Bell pairs are affected by depolarizing noise, then there is a fidelity threshold such that the final output state satisfies a constant fidelity. So our work is essentially that work of Persigors did, but we analyzed the case where the entanglement distance is actually exponential in square root of m. And we also proved that if the local stochastic noise has strength less than this threshold, this process is fault tolerant. Okay. For proof idea, I think it is very good to know this single-shot decoding of surface code. So this is nothing really new, I guess, but so what we did is suppose we have an arbitrary logical surface code state which is affected by local stochastic noise, and what we do is use the same triangular measurement pattern, and then the post-measurement state is close to the original state psi. And this work was done by Mazurek or Litinsky in more restricted error model. And the proof technique is just use the idea by Fowler in 2012. Basically, you use all the classical measurement outcomes to compute syndromes, and you find minimum perfect matching. And you can do the combinatorial analysis to find the upper bound of the probability of logical errors. And our proof is simply using this very long decoding graph instead of this triangular one. Yeah. And another contribution from our side is we can interpret the Persigors work from left column to the right column as a combination of preparing cluster state and measure the intermediate black qubits to generate this surface code encoded Bell state, and then applying our single-shot decoding of surface code. Okay. Okay. So in summary, we proved that there is a necessary size of repeater stations, which is m is equal to omega of log d. But we showed that there is a scheme for fault-tolerant entanglement generation using only m is equal to O of log square of d qubits. And we stressed out that there is still a logarithmic scale gap between those bounds. So I believe it is still an open problem, which is pretty much interesting. Yeah. Thank you for listening to my talk.
questions. There's one over there.
Thanks for the nice talk. I'm wondering if our scheme can be generalized to 2D geometry. It seems like the main idea is like using each slice is a 2D surface code. So I'm wondering if like for like the whole thing is 2D. Is there any idea how to do that?
So you mean, so we have each cross section is 2D graph state, right?
Yes.
Yeah.
So what about like each slice is 1D and
Yeah. So our theorem on necessary size of the repeater station does not really rely on this geometrical dimension or something, but it would be interesting, yeah, if we investigate what is the restriction regarding the dimension of the structure.
Cool.
Yeah,
Thanks.
Yeah.
More questions? I can interject a question while you think about other questions. So your structure of the repeater seems to be kind of like arranged linearly, so that somehow you have the stations next to each other, and I sort of got at least a feeling that the information is propagating somehow that way. In like the traditional repeater setup, you kind of like arrange things among pairs, and then you connect those pairs up, so it has a more like more like a tree structure that expands faster. Do you have any thoughts on this?
Yeah. Okay.
How does your work relate to traditional work on quantum repeaters? Is maybe the short.
Yeah. Okay. So for this work, we only need to transfer our classical measurement outcomes to either one of the endpoints. So
Yes.
we don't. So every entity is just send the measurement outcome to the end, maybe, and then in this side we compute the sort of matchings to compute the z alpha and x beta, which is the logical polys.
Right.
Yeah, but I don't know, like,
apply to other architectures. So maybe another way of formulating it. Or does it apply to the architecture outlined? Or
I don't know, like, but if it would be interesting if we restrict on the how to say, the direction of the transmission of the classical data. I don't know. Yeah.
okay.
Yeah.
Okay. Thanks a lot. Are there any other questions from the audience? There's one over there.
Thank you for your nice talk. My question is, in your work and in other previous work, the triangular measurement patterns are used. So, are there any physical intuition about that measurement pattern?
Yeah. So idea is like here in this 2D surface code, you're actually correcting one of the logical error, let's say x, with this decoding graph, and the other logical error like z with the other decoding graph. So this might be an answer to your question about what is the intuition with this.
Okay, thank you.
Yeah.
That's not the case. I suggest we thank all of our three speakers.